we know this is true. Then remember our goal. This is what we need. So we have to use our assumption if this is true. So then we may say, both sides added by k plus 1 squared. So then this is our assumption. So we will have a 1 squared plus 2 squared plus 3 squared plus dot 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 k squared plus k plus 1 squared, and then k plus 1 2k plus 1 over 6 plus k plus 1 squared. Okay. Now comparing our goal, let me fold it. Comparing our goal is what? Our goal is this. Left hand side equals right hand side. And here we have a left hand side already by adding what? K plus 1 to the assumption. Because assumption was k, the statement is true for n equals k. And then we add k plus 1 squared to the assumption, we get that. Now comparing this one and the one right here is that we have a left hand side already. They are the same. On the right hand side, they are not the same. So if right hand side they are the same, then we are done. Okay, so our business is what? Is to change this one to this one, or changing this one to this one, or is what? Changing this one to somewhere and also changing this one to somewhere to see they're actually the same. Okay, so that's our business. Now let's see how are we going to do that. In this way, in this case, we will change this to a certain form, we then stop, and then we will work on that, we will stop, and then compare. We will see they are actually the same. Okay, that's the approach. Now, look. We want to add those two together. Here there is a 6. So we put 6 here and 6 here. Then we get the same denominator. Okay. Now, there is a k plus 1 here. There is a k plus 1 here. Now, this is squared. So we may pull something out. That will be k plus 1 over 6 out. This is in comma. And then, I want to do more at one step. Yeah, maybe I'll do more steps. In this way, you can keep track what I'm doing. K times 2k plus 1, because k plus 1 over 6 is out. So the front one, the first expression has that. The second expression has 6 k plus 1. There is no squared because 1 of k plus 1 is out. Okay, so what do we have? We have a k plus 1 over 6, and then k times 2k, k times 1, 6 times k 6 times 1. Distributive property. Okay. So we have a 2k squared plus k plus 6k plus 6 times 1 is 6. Okay. Yeah, you may do one more step. That's k plus 1 over 6. And then right here, you then have a 2k squared. And remember, here there is a 1 in front of it. So 1 plus 6 is 7k plus 6. Okay? So right hand side, we go up to this far. But you know, comparing this one with this one, as our goal is still there is a distance. We don't know if they are the same. Now look. Here there is a 6 and k plus 1. That's the same. So we want to use this one times this one. And we want to end up this product should be that. Then we are done. Okay? Now, let's keep working on that. The right hand side, this one, k plus 1, and the k plus 1 plus 1, 2k plus 1 plus 1 divided by 6. That's right hand side. Okay, again, we don't want to work on that. We want to work on those two. Okay, now how? We keep k plus 1 over 6 up. And then inside here is k plus 1 plus 1, there's k plus 2. Okay, now 2k. To save the work, you do 2 times k, 2 times 1. This will give you 2k plus 2. Okay? And then plus 1, so you have a 3. Okay? So let me write would be 2k plus 3. Okay? Alright. Now, you FOIL this out to see what's going to happen. K plus 1 over 6. FOIL k, 2k is 2k squared. And then outer product is k, 3 is 3k. Inner product is 2 times 2k, so it's 4k. The last product is 6. Okay. Okay, now you can combine those two together because this is 3, this is 4. So what do we get? K plus 1 over 6, 2k squared plus 7k plus 6. Okay, now you see they are the same. Okay? Yeah. This one and this one are the same. Then you may say, I'll take this one away. And then I keep moving in this way. You may write here, hence 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared plus k plus 1 squared equals k plus 1 k plus 1 plus 1 2k plus 1 plus 1 divided by 6. So what do we get? What we get was, assume the statement is true for n equals k. We assume this is true. Then we have proved they are equal. So you might say then the statement is true for n equals k plus 1. So recall that we started with n is 1, and then we have a statement is true, and then we assume n is k is true, and we end up with the statement is true for n equals k plus 1. Now, you can go this loop again and again and again. What do I mean by that? K can choose 1, it tells us, then k plus 1, we got 2, so n equals 2 is true. And then again, k then can choose 2. If k is 2, then the statement is true for n equals 2. We will reach to 2 plus 1 is 3, so the statement is true for n equals 3. And then again, k can choose 3, so the statement is true for n equals 3. Go through this process, then we will find out statement is true for 3 plus 1, so n can choose 4. So this loop goes again and again and again. Then you will see the statement is true for all natural numbers. So down here, then we can conclude, hence, or we have hence then, so you may say, so the statement is true for all natural numbers. Okay, and that's the mathematical induction. Using mathematical induction, we can prove that. So there are 3 steps. Step 1, you want to have your floor. Okay, you test one value, n equals 1, and found this is true. The statement is true for n equals 1 at least. So step 2 is, this is step 1. Step 2 is, assume the statement is true for n equals k. Then you want to prove the statement is true for n equals k plus 1. This is the longer part. So test, assumption, then step 3 is longer. Okay, you want to prove this is true. Then you can make the conclusion. Okay, so here will be the conclusion. Alright, okay, that's the end of the lecture for this question. I'll see you next time.